Good afternoon, Year 11, Year 12. What I'd like to do this lesson is go through something called entropy. Now, entropy is the state of disorder or the state of chaos within the system. Now, why do we need to know about this? Well, it comes from this question at the top of the page here, is why do chemical reactions take place? So, for example, if we have magnesium and copper sulfate, when we add the two together, why does that reaction happen spontaneously? Now we know that copper sulfate magnesium displaces the copper from the copper sulfate to form magnesium sulfate solution, and copper is formed. Now this is an exothermic reaction. That should give you a little bit of a hint about why that would take place. Now normally this would be because the activation energy for this reaction is actually reasonably low. However, if we look at the case of the second two examples of citric acid and sodium hydrogen carbonate and ammonium nitrate, both of those are endothermic reactions. So heat is needed to be provided from the surroundings into the system in order to get that chemical reaction to occur. But it does, and the reaction is quick enough and is spontaneous enough for that reaction to take place under normal conditions. So there must be something else that affects the spontaneity of a reaction rather than just the enthalpy, and that is where the entropy of the entropy comes into this. Now, for those of you that do an A-level physics, you recognise the term entropy. It's the amount of chaos within the system. In the case of A-level, and I'm just realising that arrow thing's getting in the way. In the case of chemistry, we don't go into as much detail on that. We talk about the entropy of a system as the amount of chaos or disorder within the system. In physics, you talk about in the number of ways in which the atoms can share the quanta of energy. So for example, that would be the number of ways of arranging the energy, which is W, and the system then tends to become disorganized, and its entropy, which is S, becomes high. So if it's a way of organizing the energy or a way of arranging the energy so that it's more chaotic, then it tends to be a higher entropy for the reaction. Now, factors that affect the entropy, actually I've summed these up quite graphically, because what I've tried to do is get you to think about this physically. Most of this is about me trying to put pictures into your head that you can understand. So substances would have more ways of arranging their atoms and energy are more disordered and therefore have a higher entropy. So going right back to year 7, if you think of the idea of solids, liquids and gases, inside a solid the particles are arranged in regular order, in other words a lattice, and they are only able to vibrate. So the movement is small, so they have low kinetic energies. The arrangement is very, very fixed, so they have fixed position. They have low energy and therefore low entropy. As we then move to a liquid, what happens then is their kinetic energy increases. They move around more, so they are, here the energy is more disorganized. The structure itself now is more disorganized, so the entropy is much larger. Converting that to a gas, the particles now are completely random, completely chaotic. They can speed up and slow down as they hit the walls and transfer their inertia to the walls and so on. So the highest energy state, or the most entropic state, is the gaseous state. Now what we then also turned around and need to do is, once we've done the idea of single atoms and solids, liquids and gases, we then need to have a look at elements and compounds. And basically the idea of elements and compounds is as follows: that because an element in a regular lattice is all the same atom, then the ways of arranging it are quite limited. And because they're quite limited, that means the number of possible arrangements and therefore the entropy is low. If we go to a compound, and I know I've chosen an ionic lattice here, which technically isn't the most disorganised, but within a compound there's a slightly larger range of choices in positions that we could have, and therefore the entropy tends to be slightly higher. So I'm trying to give you two examples. So we've got solids, liquids and gases change the state. Now I'm doing elements and compounds, which is the arrangements of the molecules. What we're then going to need to do is move on to the idea of pure substances and mixtures. And I've got here two containers of gases. So this is very high entropy for a start. And then we are mixing the gases together. And the fact that the gases mix together means that they actually make the overall entropy of the container much more chaotic, because their positions can affect each other randomly, alter each other's courses and so on. And we can't say that only the white particles that appear on the left hand side, they will appear randomly. If we also look then at the liquid, and this is dissolving, we've got a solid being added to a liquid, and the particles of the solid, once it's in solution, are completely randomly spaced. And because this is a liquid, the particles move, so therefore the particles of the solvent and the solute change place, so the chaos of the system is much higher again. So all of these are factors, and they keep adding up to the entropy. So the entropy itself, if we've gone through this, is the idea of the chaos of the system. The more chaotic it is, the more disorganized it is, the higher the entropy. Now you will notice here, I've done this as a scale, and I really should put an arrowhead on top of this. We've got this as a positive scale. So as the entropy increases, the value of it will become more positive. So at this bottom corner here, we have a point where technically you can have zero entropy. Now this is nothing to do with, oh, it's a solid in its standard state, it's got a zero entropy. No, the only way that you can get zero entropy is to remove all energy from the system and stop the particles from moving, so there is no chance of them being disorganized. And in order to do that, what you need to do is drop their temperature down to absolute zero, so they have no energy at all, they are not moving, and they are completely stationary. So that's the only point at which you have zero entropy. Any temperature above zero, and there's going to be a slight vibration, so they can be in slightly different positions as they vibrate back and forth, or as they turn to gases, they can move around, liquids and solids and move around. Now what this graph is showing, this is slightly different from what we've seen before, because normally we've had temperature on this axis, and then another value on this. We've got temperature across the bottom, entropy. So this is as the temperature increases, you can see here that the entropy of the system increases. Now we get to this point here where the temperature no longer increases, but the entropy of the system does. This is where this is the enthalpy. Now I've got to get this right. Is it the enthalpy of? Can't remember. I need to check that. This is the entropy. This is the point. So enthalpy. This is the point where we have a change of state to a liquid to a gas, from a solid to a liquid. So this point here, what is happening is all of the bonds that are holding the the atoms in place are being broken, and then as they are broken, the particles are then starting to move, but they are still held in place by the weak intermolecular bonds between the liquid molecules. So the entropy is increasing because the bonds are being broken. However, the temperature doesn't increase. It doesn't increase until all the bonds are broken, and then it's in the liquid phase, and then the temperature will start to rise. This happens again as when it turns from a liquid to a gas. This is called the latent heat of vaporization, and at this point all of the bonds being broken between the liquid, and it then turns into a gas, and at this point this will carry on indefinitely as high as the temperature goes, and possibly another state change right up here as it goes from a gas into a plasma. But that's A-level physics here. Okay, so you get this idea that increasing in disorder of the system increases the entropy. Now, that I said here it's a positive value, so delta S should be positive if it's becoming more disorganized. So as the entropy increases, the amount of disorganized, and it should be a more positive value. Now, we've known this repeatedly now, the triangle means difference of or changing. I've added a little bit of notes here then and said basically the things that increase the entropy of the system is changes in state. So solid to liquid, the entropy is higher in a liquid. Liquid to gas, the entropy is higher in a gas. The other one here is an increase in the number of molecules in products and reactants. So for example, I've done this on the next page. What I've done is I've given you two examples here. The first example is ammonium chloride. Now ammonium chloride is a solid. That thermally decomposes into hydrochloric acid and ammonia. Now ammonium chloride is a solid. Hydrochloric acid, when it thermally decomposes, is a gas, so is the ammonia as a gas. So we've got straight away, we've got an increase in entropy because it's going from a solid to a gas, which is more disorganized. What you've also got is one molecule of reactant and two molecules of product. So you're also increasing the number of molecules of the product, so it's gone from 1 to 2, so that increases the entropy of the system as well. So that definitely is an entropy. Positive correlation, so it's both of them are increasing it. Whereas if we look at the second example, what we've got here is sodium solid plus chlorine as a gas. When they combine, it forms sodium chloride, which is a solid, or sodium table salt. So in this case we've got a problem because we've got a solid and a gas turning into a solid. So in this case the gas turning into a solid and the solid staying as a solid, I would actually say gas turning into a solid, it's becoming more organised. And because it's becoming more organised, delta S will decrease. The second thing we've got contributing towards this is I've got here 2 moles of reactants, 1 mole, 2 mole, going to make 1 mole of product. So I'm decreasing the number of molecules within the system as well, so that will also make it less disorganized. So the delta S of this will actually be negative as well. So this is a way of predicting it. Sometimes you can predict it and it's quite easy. Other times, as I'll show you when you do the example booklet, there are 1 or 2 where you can't make a prediction because one would say it become more positive, the other one becomes saying less positive, and so therefore you have to make that judgment that you can't make a prediction. Now to calculate delta S quantitatively, which means getting a value from it, it's quite simple. To look at the delta S of a reaction, you take the products, delta S, the sum of the products, delta S the products, and take the sum of the delta S of the reactants. If the final value is positive, it has become more entropic. If it's negative, it's become less entropic or more organised. I'm trying to use the opposite terms there. Now, delta S is measured in joules per Kelvin per mole. Big problem with this. This joules will be the biggest reason for you losing marks on any of these questions. For the simple reason, what we've used so far is our example. Whenever we've used joules, we've used delta H, which is the enthalpy, which has been measured in kilojoules per mole. So if we have any equation that uses or asks for us to use delta S and delta H, we have to unify as one value. So we either have to use kilojoules per mole or joules per mole. Now I would suggest that you use kilojoules per mole because it's easier to multiply the number of joules by, divide the number of joules by 1,000 to transfer it into kilojoules. That's just the way I do things, it's up to you. Other thing, and this is the big part of this, if I get this value here, and this is a capital K. When you talk about kilojoules, it's a lowercase k. And that is quite hard to distinguish between the nodes. Now, let's have a look at the workbooklets that you've got and look at the example that you've got in here. Okay, this is where it says calculating the entropy change. What I'm looking at this is a straightforward calculation. You've got the equation here. You've got 1 mole of ethanol plus oxygen goes to make 2 moles of carbon dioxide and 3 moles of water. So this is straightforward combustion of ethanol. Now you're given the values, and you will always be given these values in the equation, so all we're going to do is use those values to calculate it. Now I'm going to start off, as I always do when I write these equations, and that is actually writing down the equation, because that's a bit tucked out away from my likings. I don't like that, so I would rather make it more central and write it down here. So I do apologise, I have to move the chair out of the way then. 3O2 G plus 2CO2 gaseous plus 3H2O liquid. Now all I'm going to do for this now is calculate the values. So I'll do it this way. If I put a line down there, it's not on that side. God, I'm making a mess of this today. The wonder why this file in there. So here I've got a value of 161, and here I've got a value of 3 times 205. So that's 161 plus 615. I've not got a calculator available, so I'll just work this out in my head. So that'll be 776, and on this side I've got 2 moles of carbon dioxide. Carbon dioxide is 240, so that's 2 times 214, and on this side I've got 3 moles of water. That's 3 times 70, so that's 4428, and that's 210. Add the two values together, that'll be 836. Now going back up to the equation at the top, I've got products minus reactants. So to work out the delta S for the reaction, I do product 776 minus 638, which is 138 joules per Kelvin per mole. Now up here it's got it written that way around. I think that's probably slightly easier to write that, otherwise you get confused on where the K is. That's a straightforward, simple question. That's nice and calculated. Do we all agree with that? And that is what some of the questions are on the next page. Now this next bit is making a prediction. We don't know the values, we are given no delta S values. We have to predict, we have to work out whether they're positive or negative. So all I'm going to do with this is do 1 and then 1 plus 2. So more products than there's more products than reactants. What is going to happen then is by producing more products, the delta S would increase. So that would cause the delta S to increase. In this, I'm then looking at this part, which is the state, and it's going from a solid to a gas So solid going to gas plus gas, and this is just me driving down my logic. And you'd have to word this a little bit better. That would also increase the delta S. So I would say so on nil, the entropy would become more positive. Okay, simple, straightforward understanding, and I'm just looking through picking the answer. Now, doing the second one, and this is one where I said we need to have a bit of a think about. I've got 1 mole of that, I've got 2 moles of that, I've got 1 mole of that, 2 moles of that. So, same number of molecules, therefore delta S equals, I'm going to put a question mark, I don't know. If it's the same number of moles of reactants as products, I can't tell you whether the delta S is going to improve or increase or decrease. Don't know. This one, I've got gas plus gas goes to make gas plus gas. I'm still stuck. I haven't got a clue. I would say, don't know on that. The only thing I can think of is, and this is where I would never make this judgment in an exam. Okay, the only thing I can think of is elements, compounds. Element there, 2 compounds there, compound there. I could possibly say element, reactant, two compounds, query mark, delta S, increase. I don't know. That's possibly the only thing now that I'm thinking of as being not a possible option on me. So I've gone through and ticked off many of those. Have I gone from pure substance to a mix? No. Have I got the same number of molecules? No. Same number of molecules on both sides? Yes. Have I got change of state? No, because they're all 4 gases. The only thing to think of is this is an element, and so you've got a compound and an element versus two compounds. That's the only thing I can think of. So I would probably say no possible prediction there, or if I would, I'd have to justify it quite clearly on this. Now I'm hoping that with the feedback I've given you there, you would then be able to go on to do task number 7 and have a reasonable go at explaining that. If you can produce the notes on this and then, if you can produce your answers to this and then find some way to upload or scan them back to me, I'd appreciate it. I'll go through your notes and mark them. Thanks very much. Hopefully speak to you all again soon.